Thanks a lot, Stefan, for organizing this great event. And yeah, thanks for inviting me to speak. It's also a great pleasure. Okay, so just to get things started, it is I view it as a little bit of my job to introduce the audience to maybe the formalism and the mathematics of quantum information, so that the next speakers will be able to show you something very interesting and very cool. Now, of course, the challenge we give in this kind of talk is that I don't get a chance to show you something cool. So I'll go a lot over the basics and I'll go slow so that I make sure that everything is clear. But some things that I'm introducing, you will sort of have to accept it as facts of life, and you're not allowed to ask too many questions on why we do things the way we do them. But of course, I mean, ask questions, and I will decide not to answer for some of them when I think it's not appropriate. But no, of course, ask questions. Anyway, so let us slowly get started. As usual, the first slide of any quantum information talk, it should tell you where this discipline sits. And it's actually a very beautiful and rich field, the field of quantum computing, quantum information in general, because it sits in the middle of three very mathematically rich and sophisticated disciplines, which are math, physics, and computer science. Yeah, and there is a lot of deep work, deep technical work about quantum information in all the three disciplines. You can really take your favorite view on this problem and try to make progress on your terms. However, I must also tell you that this talk has no physics whatsoever. I'm also not a physicist, so you're not allowed to ask me any questions about physics. This talk is firmly rooted in computer science. There's going to be a little bit of math. To get by with the basic things, but we'll take mostly a computer science perspective on quantum information. Again, it's nice to know the physics behind this, but it's this talk, and in general the way we typically do quantum information, it also shows you that it's not necessary. I mean, you can sort of accept the model the way it was given to us by God, and or whoever invented it, and just do math or algorithms with it. So you don't really need to have any physics background, definitely to understand this talk. Okay. Good. So if everybody is on board, let me start with one slide of review of linear algebra. I think you all know these things, but I'll just slowly go into it so that we all get the notation straight, and then later on we can do slightly more sophisticated things. Okay, so just a brief reminder: a complex number is a combination of two real coefficients, where I is the square root of -1. You all know this. Just again, small reminder: when we talk about the conjugate of a complex number, we talk about the complex number with the imaginary part flipped. Okay, so we put a minus sign with the imaginary part, and that's the operation of taking the complex conjugate of a complex number. Okay. You can actually define a norm for a complex number, which is the square root of the sum of the squares of the coefficients. Now, note that if you don't have an imaginary part, this is just the standard definition of the absolute value of the number, so it's good, it generalizes it. And I'll tell in a minute why we do things this way. Now that we have a notion of a norm, we have a notion of a conjugate, we can also generalize the usual inner product between two vectors. So if you have two vectors, psi and phi, we say that their inner product is the standard inner product, so the standard sum of the product of the coefficients, except that one of them is conjugated, like this operation here. And similarly, we can also define the matrix conjugate. And the matrix conjugate is just is this little dagger symbol here. Is just the conjugate transpose of a matrix. Okay, so if you see the indices here are swapped, meaning that we are transposing the matrix, and each coefficient of the matrix is again conjugated using this operation here. Okay, just to set up notation. Good. So why do we do things this way? Again, I think all of you know this, but just as a small reminder, the point is that if you think of the complex plane, the plane where all the complex numbers are contained, essentially the conjugation is really just the reflection across the r-axis. So it's just literally this operation, we are flipping the bit. And now in this view, it becomes quite natural to use this notion as the notion of norm, because it's really just the standard Euclidean norm. Okay, so it's really literally the length of this vector in this two-dimensional plane. Okay, so it's geometrically you can think of it this way. All right, done with complex number. Actually, okay, now that I've gone through my slides, I can also tell you that although formally you need complex numbers to study quantum mechanics, for today's talk and in general to get an intuition of what's going on, actually complex numbers are not really necessary. You can just pretend that everything is real. If you're not comfortable with complex numbers, just pretend that everything is real, and you'll sort of get the right intuition. Okay, and of course, in this case, if everything is real, this operation doesn't do anything. Okay, then you get the standard inner product and standard absolute value. Okay, so good. Okay, with that out of the way, I can get started finally with quantum computation. Quantum information. So again, we have to sort of now take a step back and essentially forget all we know about classical computation, classical information, and so on. So there are some basic facts that we don't normally think about that we have sort of hardwired in our brain, like the fact that the basic information, the basic unit of information is a bit. Okay, that's 0 or 1. We don't normally think too much about it, but it's there, and those facts are just wrong in quantum mechanics. So we have to take a step back, forget everything we know about the usual computational model, and start from scratch. So where do we start from? We start from the very basic unit of information, and the very basic unit of information, which is the quantum equivalent of a bit. It's a qubit, yeah? So the formal definition of a qubit is just a unit vector in the complex space of, in the two-dimensional complex space. Okay, so that's our definition of a qubit. You're not allowed to ask why it's defined that way, you have to just take it as a fact. This is our definition of a qubit. A unit, I repeat it because it's important, it's a unit vector in the two-dimensional complex space. Okay, so that's what we operate with. And now, this gives me a great opportunity to introduce everyone's favorite Dirac notation, which is this beautiful little brackets here, which are very, very popular and very useful in quantum mechanics. At first, it's a little bit hard to get used to them, but once you start working with them, you start appreciating their usefulness. And it's literally just it's called also the multiplexer. It's essentially whenever you're taking you see a number here in between these two in between these two strange brackets, you have to think of the unit vector. The standard basis vector where the 1 is at the position considered by this index. Okay, so for instance, this vector is 0 everywhere except at the 0th position, which is here, and this 1. So we start counting from 0, 0, 1, blah blah blah. Yeah, same here. This vector is 0 everywhere except at the 1st position, and since we start counting from 0, the first position is this one. Okay. Of course, this is not limited to 0 and 1. You can put any number here, and you get the corresponding standard basis vector. Okay, this is a useful piece of notation, and armed with this notation, actually we can, without loss of generality, take any qubit and rewrite it in this form. So any qubit has denoted by psi, and it has a component on the 0 vector and a component on the 1 vector. Yeah? And these are alpha and beta are two coefficients, which are called amplitudes, yeah, for reasons that we won't explore in this talk, but just remember these two things are called amplitudes. And as we said before, since this has to be again, by definition, this has to be a unit vector in C-square, alpha and beta are complex numbers, and the sum of their squares of their absolute value must sum up to 1. Okay, this is just a mathematical way to rewrite this condition. Okay, so far I haven't done anything esoteric. Yeah, just rewrote things in a little bit of a strange notations. Good, and we can say that it could be possible, for instance, that this alpha is equal to 1, in which case we get exactly this state, or that this beta is exactly 1, in which case we get exactly this state, but they don't have to be. Yeah, there is a whole spectrum of amplitudes in between. Yeah, and we'll see examples of qubits, but alpha and beta don't necessarily have to be 1. As long as this condition is satisfied, you can take your favorite numbers. And again, one bit of terminology. If the amplitudes, if both amplitudes are non-zero, so if there is like a non-zero component in both amplitudes, we say that the qubit is in superposition. It's in the superposition between these two states. Yeah, so that's what it means to be in a superposition. Okay. Good. Good. Okay. So and now maybe again, since we are at the very first 10 minutes of this talk, let me take it slow and reflect a little bit upon this intuition and why this is a definition that is somewhat analogous to what we know classically. Classically means without quantum. Yeah. So in our good old probability distributions and so on. Okay, so the basic unit of information in classical mechanics is just the bit. Yeah, it's a variable that is either 0 or 1. So it looks quite different. It looks really different from this unit vector in the complex space. And so you might be tempted to say, oh wow, that's where the powers of quantum mechanics come from. But actually this intuition is wrong. A more fair comparison is not with a bit, but it's actually with a random variable. Okay, so in classical computation we are allowed to make random choice. We use this thing all the time, especially in cryptography. Yeah, so things are not just 0 or 1, but they can be 0 with some probability and 1 with some probability. So really a fair comparison with a qubit is not with a bit, but is with a binary random variable. Yeah. And of course, a binary random variable is either 0 or 1 with some probabilities. So probability p and probability 1 minus p. And of course, it better be the case that these two probabilities are both positive and they both sum up to 1, just by virtue of being probability distribution. And again, nothing stops me from using this strange notation to write this random variable. Again, it's a perfectly valid notation. In this case, you see the difference. The only difference is that alpha and beta are not required to be complex, but like positive reals. Yeah. And I'm not requiring the sum of the squares to be 1, but just the sum to be 1. Okay? So this is really the difference. And if you want to think about it in geometric terms, these are units in terms of L1 norm, whereas these are units in terms of Euclidean norm, L2 norm. Okay? So this is really the difference between what we can do with classical probability distribution versus quantum bits or qubits. Okay? So it's a little bit more subtle than the comparison before. Okay? Good. I hope everybody's on board with this. Now, of course, one qubit is not particularly useful to work with. We want to actually be able to extend the space of one qubit. Yeah. So if all we had was one qubit, we would just have two complex numbers, and there seems to be not a lot of power that we can get out of this, right? So we have to actually be able to extend our states. The same way as we extend bits by concatenating them into strings, we have to be able to extend qubits to concatenate them into larger quantum states. Okay, and then now exactly what I want to show you is how to do that. So think for simplicity that we have 2 qubits. Yeah, so psi 0 and psi 1. Again, without loss of generality, they have this form here. And then I want to consider the system that describes both of these qubits simultaneously. Yeah? So of course, now my 2-dimensional complex space is not large enough to contain these two qubits. What do? I just take the ambient space of these 2 qubits to be the tensor product of these 2 complex planes. Okay? Again, this operation of taking the tensor product to consider 2 qubits is nothing special to quantum. If these 2 were 2 random variables and you want to consider the entire space, you would also take the tensor product of the space of the random variables. Okay, but note that the dimension stacks up multiplicatively once you consider these 2 qubits. Okay. So the correct way turns out to describe the joint system between these 2 qubits. So again, physically you have 1 qubit here, 1 qubit here, and now you want to look at them together and you want to describe the system. The right way to do it is really to just put a tensor product sign in between them. Yeah? And then you will define the larger quantum system to be the tensor product of these 2 qubits. Okay? Again, you have to take this as a fact, but you can convince yourself by classical analogy that this is the right thing to do. This is just a bit of notation that I want you to remember, which is a little bit, I think, maybe counterintuitive. But sometimes we write this to denote the tensor product between 2 qubits. Sometimes we just omit the symbol, and sometimes we just omit the parentheses. But these 3 things mean the same thing. I mean, it's an equality in the sense that these are defined to be the same thing. Okay. Sometimes it's more convenient to use either of them, and so we'll switch back and forth. I'm showing it not because I'm lazy, but because this is often done in the literature, so it better be the case that you learn. Good. So as I said before, if you like to have some physical intuition about what's going on, you can think of each qubit sitting in a different register. And then the act of looking at both registers simultaneously requires us to enlarge the system by taking the tensor product of the 2 spaces. Again, this is a very natural thing to do. If you think about it for 10 minutes, you would come up with the same thing. Yeah? Everybody convinced? Good. But of course, this was just an example, right? This is a 2-qubit system. Nothing stops me from keep adding qubits. So once I know how to add qubits together, I can keep doing it, right? And in fact, nothing stops me from introducing more qubits into the system and consider larger and larger space. Oh, yes?
What's the difference between the tensor product and a matrix product?
Sorry?
What's the difference between the tensor product and the matrix product?
Well, these 2 are vectors, or not matrices.
Right, but okay. I'm not sure if everybody knows what the tensor product is.
I don't. Oh, okay. Does anybody not know what the tensor product is?
So let me put it a different way. So when you take C square, tensor C square, you get C4.
Yes.
But also C square plus C square is C4, correct? If you take a direct sum.
The direct sum, yes.
So what's the difference? So in this case, it seems that you get the same thing. So what is the difference between a direct product and a tensor product?
I think in terms of, so you're saying that it should be a direct sum, or?
No, I'm not saying. I'm saying that those are 2 different things, but it's not clear just from the notation that. I mean, I know the answer. I'm not asking for myself. I'm asking for the audience.
I see.
And I think that was perhaps the spirit of your question.
So if you take C3 and C squared, then the direct sum is C5. You take tensor product, this is C6, because the basis, so for the direct product, the basis is basis plus 1 plus basis for the second, yes? And for the tensor product, the basis elements are the product, so 1, 1, 1, 2, 2, 1, 2, 2, 3, 1, 3, 2.
Say all over.
Okay, so the difference is, for example, in the basis. So the basis of the product, so I have like C3 and C square, yes? Then the basis for the direct sum has 5 elements, because it's the basis elements for the first and the basis element for the second. And for the tensor product of C3 and C square, the bases are the products of basis elements. Yes, so 3 times 2 is 6. So this is like the most simple explanation.
Thank you. Does that answer your question? Good.
2 plus 2 is the same as 2 times 2.
I see, okay. I see. I think I understand now good. So, okay. I think I understand now the possible confusion with this slide. So this is correct, but what Daniele was pointing out is that maybe another way to do this would be to take the direct sum of these two spaces. In that case, you would get the same thing, just because 2 plus 2 equals 4, but also 2 times 2 equals 4. But it turns out that the right thing to do is actually to take the product, and that shows up when you take something which is not 2. And in that case, you start seeing the difference. Thanks also for the gentleman on the very back. Okay, more questions. Great. Okay, so great. Now that I've introduced, now that we're all on board with tensor products, yeah, nothing stops me from keep doing this operation over and over and over, right? Up until I get, you know, a state of a much larger, which lives in a much larger space. Yeah. So now I'm ready to introduce the first postulate of quantum mechanics, which states that a quantum state is a unit vector in a particular Hilbert space. Now, the word Hilbert space is not particularly important here. If you don't know what it is, it doesn't matter. You should think of it as just a complex vector space. They are the same thing if the dimension is finite. And will be throughout this school, so I think. So you can just really think of it as a complex space. And you should really think of this as just literally the definition of a quantum state. Yeah, it's not a theorem, it's literally just a definition. A quantum state is just a unit in this Hilbert space. That's sort of the basic unit of information that we will learn how to operate on, and we will learn how to compute on this state. Okay. Now, as we said before, if we start by adding qubits by qubits, if you have a little n qubit states in the end, so we repeat this operation of adjoining qubits in a system n times, then we end up with something which is capital N, which is 2 to the little n dimensional space. But the amount of sort of registers that we have is still little n. It's just to describe the entire state of the system, we need capital N equals 2 to the little n complex numbers. Okay? Again, this is just a postulate, so there's no proof here. It's just a definition. Good. And now of course, now we need to generalize a little bit the notation that we had before. It turns out that actually there is nothing special about 0 and 1. I can take, as I said before, any number and you know, introduce this notation for any of these numbers. The name of this basis, you can check for yourself that this is a basis of C power n, and the name of this basis is usually referred to as the standard basis or the computational basis. Yeah. So this is just a convention that we use because it's convenient for us human to read. But it's not. In principle, you can take a state and represent it in any basis of Cn. Right? So it's just a convention that using this basis is just a convention for us to read. But of course, nothing stops you from using a different basis. Okay? And as before, we can take any quantum state and write it as a linear combination of these vectors here, where these are again complex amplitudes. And in order to make this a unit, we have to once again enforce the condition that the sum of the absolute value squares sum up to 1. Yeah? So this is just a generalization of what we have seen before. Yes?
Okay, if we look at the next to the last row, usually we have to write 0, 1, and -1 not as decimal or ordinary numbers, but like binary numbers.
So in that case, so you mean you can have the binary decomposition?
You usually write small n bit number.
Good. You can do that, but that's actually the same thing, because if you recall by my notation before, that's just taking the tensor product between the bases, right? And so it's literally the same thing. Yeah, but yeah, good point.
I just want to say that based on the last line, you cannot say that the quantum state is a unit vector. It's a vector in Hilbert space.
So that's my definition of a quantum state.
A quantum state is a vector in Hilbert space. You can write it using unit vectors, but it's not a unit vector.
Well, but I need to normalize. I need a condition to normalize states, right?
Yes, you can normalize it, or you can write it using unit vectors, but you cannot say that it's a unit vector. A quantum state, in general, is a vector.
Sure. But I mean, I guess maybe this goes a little bit in the direction of sort of how you model what's your model of computation. So in my view, again, I take this is my definition of a quantum state. Yeah. So again, it's not something that is a theorem or anything. It's just by the way I define a quantum state, and then I'll show how to compute with this. Now, clearly, you can have I mean, there's what's your Hilbert space? Like once you have molecules and particles, I mean, you can define things the way you want, and it's just the fact that it's a unit is just a convention for us in order to compute effectively with it. You can always rescale things up and down so that things are a unit.
Thank you.
I always thought that the pure quantum state is just a tensor product, just a simple tensor.
Say again?
Pure, isn't it like just a tensor product of, like irreducible tensor, isn't it?
A pure state doesn't have to be a tensor product. Okay, so okay, I'll get to. I think you're thinking about entanglement. I'll get to it in the next slide. Maybe let me take this question in a minute.
Just one last question. Are you normalizing just the length, or are you also normalizing up to multiplication by any complex number, so rotations on the complex?
So I'm just a state, you mean?
So if you take a state and you multiply it by I,
yes.
Is it still the same state?
Yes, it's still the same state. So okay, I didn't want to get there. But since you brought it up, so in this notation of states, it turns out that if you add what's called a phase to the state, the global phase, for instance, multiplying it by I, it turns out that these two states are mathematically equivalent. They are physically the same object. Okay. To see why that's the case, you would have to introduce the formalism of density matrices, which I don't want to do. But for the moment, you can think of it as, if you have like a global phase in the state, that global phase doesn't matter. So you can sort of always ignore it. As long as it's a unit, then everything is fine. Yeah. Thanks.
Is it has to be the power of 2? Hello?
Yes.
Is this has to be the power of 2 since
it doesn't have to be a power of 2.
You tensor product 0, 1. It is a vector of 2 dimensions.
Right. So it's not every quantum state is a tensor product of qubits.
Okay.
We'll see it in a minute why. This doesn't have to be a power of 2. I just took it for my own convenience. But sort of the way we constructed before the quantum state, the way I told you, it will be a tensor product of qubits, but in general, it doesn't have to be. And we see in a minute why. More questions? Good. So, I hope everybody is on board with this definition. Quantum state, unit vector in a Hilbert space, my definition. Good. Now let's go on to the point that I think some of you have thought about a little bit, which is entanglement. So as I showed you before, I constructed a quantum state by adjoining qubits to the system. And then, when I adjoined one qubit to another, I take the tensor product, then I join one qubit, I take again the tensor product, and I end up with a larger state. Okay? So you might be tempted to think that any state, any quantum state, can actually be decomposed into tensor products of smaller dimensional space. Yeah? So we can ask about the reverse operation. So let's say we have a quantum state, yeah, which is, by my definition, a unit vector in some n-dimensional Hilbert space. And let's say even the n is a power of 2, just to avoid dealing with division problems. So let's say even that n is a power of 2. Can we always decompose a quantum state into tensor product of qubits? So actually, the answer is no. Yeah? So it turns out, and we'll see examples, that you cannot always do the reverse operation. You cannot always take a quantum state and decompose it into a tensor product of smaller Hilbert spaces. Yeah? And if that's the case, then you can call your state entangled. Yeah? So now you know what the word entanglement means. So this is the most misused word in the history of Hollywood movies. Now you can point out all the errors which is all the time, basically, that they use the word entanglement wrong. Okay? So entanglement is a state that it cannot be decomposed as a tensor product of a smaller Hilbert space. Now, of course, entanglement changes also depending on what kind of register you're considering, right? So you could consider a bipartition between, two particular sets of register. In that case, the state may not be entangled, but the same state, maybe considering a different bipartition, could be entangled. So entanglement is a concept that comes across a cut of the register. Yeah? So it depends on the kind of bipartition that you are. Bipartition, for simplicity, you can also consider multipartite entanglement, but like it's a concept that involves splitting your state in half somehow. Okay, is that making sense? Good. Yes.
Just a very naive question. So, how can I think of this? So, if I take all the qubits and their tensor products or the combinations and see which results I get, does that basically just mean that if I did this operation to all of them and looked at this set, that the set that are these that we cannot decompose, that is basically, we do not get the whole set if we just... Exactly, if you just consider the tensor product between two-dimensional states. Yeah, exactly. Okay, thank you.
We'll see an example in a minute. Okay, so let me actually show you examples, and then we hopefully get a better intuition. Okay, so now I'm just going to consider single qubit states. We already seen two examples, the 0 and the 1 state. Here are two slightly less trivial examples. The plus state is the state that has equal amplitude on the 0 and 1. Yeah, you can check for yourself that is a unit. It's called a plus because there is a plus here, and very unimaginatively there is the minus state, which has a minus here. Yeah, you can also check for yourself that this is a unit. So it's a valid quantum state according to my definition. Okay? Again, these are, as we learned before, these are states which are not, where both coefficients are non-zero, so we can call them superpositions. So these are superposition between 0 and 1. Okay? this is easy. So let's go to maybe slightly more complicated example and consider 2 qubit states. Yeah. So this is a valid state. It has equal amplitudes on all possible coefficients. Yeah, and it may look like this state is actually pretty entangled because there is quite a lot of amplitude spread out all over. Turns out that this state is not entangled, and precisely because I can write it as a tensor product of plus and plus. Yeah, you can do the math. Here's the definition of plus. You can do the math and see that this is actually what you get by taking the tensor product. And so this state is indeed decomposable into the tensor product between 2 single qubit states. Yeah? So it's not entangled.
So how come where the minus Sorry, I cannot get it. So you take a tensor product, where did the minus go?
No, so these are unrelated.
This is plus plus, sorry. Oh, okay. Sorry.
Plus plus. So yeah, if you had the minus, you would get some minuses. So.
Sergio, so I'm not sure I understand if this definition of entanglement, does it depend on the choice of the basis or does not? Because, so you start from the qubits.
Yeah.
You take the tensor product, okay? Now, you can define the tensor product in a way that is independent from the choice of the basis. So you have this bigger Hilbert space. Now, you can have any basis for this Hilbert space. Now, a vector in this Hilbert space, a state in this larger space, whether it is entangled or not, does it depend on the fact that you started from a specific decomposition in qubits?
Yeah, it does not.
It does not.
It does not. So no matter how you sort of choose your basis, you should not be able to. Yeah. We'll see one example of an entangled state now. It's the classical, sort of the most traditional example. This state is called the EPR state for reasons that will be clear in a bit, if we get there. And this is not that it looks a little bit smaller than this guy, but it's really a 2-qubit state. Yeah. And you can check for yourself that this is actually a unit, so it's a valid quantum state according to my definition. Yeah. But no matter how hard you try, you will not manage to write this as a tensor product of 2 qubits. Okay? You can try and see why it fails. So this state is indeed called entangled. In fact, it's the maximally entangled state. Okay? This is just an example. Of course, you can cook up more complicated examples. Good. Fantastic. Now, I want to do some remarks on notation, and then I'll sort of move on to maybe more interesting things, like how we can manipulate these quantum states and how we can compute on them. Okay? So this notation is that I used before is actually called the ket notation. And the notation, the reverse, where you put this peak on the other side, is called the bra. And mathematically, this corresponds to taking the conjugate transpose of your vector. Right? Again, recall the definition of conjugation from the previous slide. Again, if you don't care about complex numbers, just think of it as a transpose. Yeah. And if you put them together, you actually get a bra ket, which is actually just the inner product between the vector and itself, and which is 1, again, according to my definition of quantum states. And yeah, it's a physics humor. I don't know why they call it like this, but it's a bracket. Okay. Okay, so a point that I think some of you were a bit confused before, or I think maybe Daniela's question was hinting at, was about pure versus mixed states. So the way I define quantum state is always about pure states. And pure state is just literally a quantum state as I define, so as a unit vector on some Hilbert space. Okay, but again, nothing stops me from actually consider classical distributions over quantum states. So maybe let's say with probability 1/2, I take this state, and with probability 1/2, I take this other state. Yeah, that's a probability distribution over quantum states. And you can actually formally consider this object. It's called a mixed state. It's in some occasion it's more convenient or it's more general to use mixed states. Throughout this class, I think there will be very little of mixed states, so you can always think of a pure state as a quantum state. But in case the word mix shows up, you know what to think about. It's always like a probability distribution over quantum states. Okay. This is just 2 remarks on notation. If nobody has objections, we can move on. Good. Okay, so we have now defined our basic unit of information. If you think about it in the classical terms, we have made very little progress. We just have essentially defined what is a bit, but we had to work a little bit harder for quantum mechanics. But now we have to show how to actually manipulate quantum states. Okay, once again, there is a law for that. It's not like we can do anything on a quantum state. And the law actually comes from the Schrödinger's equation. So we need a way to turn a quantum state into another in such a way that it doesn't break the laws of quantum mechanics. And for that, we need to know what are the laws of quantum mechanics. So what are the quote-unquote legal operations that we can perform on a state according to the laws of quantum mechanics. And again, this is a postulate, it's not a theorem, right? I'm postulating that quantum states must evolve according to the Schrödinger's equation. Okay, this is this thing here. This is a Hermitian matrix. It's called the Hamiltonian for some reason. And if you have seen this equation in a different form, you should not be worried. I just took the Planck constant to be 1. This is mostly a remark for the physicists in the audience. I know there's at least one of them. And yeah, anyway, but if this doesn't mean much to you, it's fine, because actually we can reinterpret this law in a mathematically equivalent way, but it is going to be more convenient for us to work with. Yeah, so I just wanted to show this so that you know what's the role of the Schrödinger equation in quantum mechanics. But now I ask you to forget about it and rather remember the following postulate, which is more convenient from a mathematical slash computer science perspective, at least for the things that we're going to see in this course. Yeah. So again, in computer science, we think in discrete units. We don't care about the fact that the time is continuous. We think in like discrete ticks of time. And in that case, it's actually much more convenient to think about unitary operations. Again, these two definitions can be shown to be precisely equivalent. So I just want you to remember this, like any legal operation on quantum states requires you to apply a unitary transformation on a quantum state. Yeah. Again, we don't know, I mean, we have to accept this as a fact of life. There is no theorem that we can prove about it. It's a fact of life. But we can see that it actually makes a little bit of sense. So let me say first what a unitary matrix is. A unitary matrix is a matrix so that if you take the conjugate transpose, recall this little dagger was the symbol for the conjugate transpose, U times U equals to identity. So that's the definition of a unitary matrix. So again, we can try to make sense out of this rule, and if you think about it for a second, it actually makes sense in the sense that unitary transformation map quantum states to quantum states. Right? It would be bad if you know, I start with a quantum state, I apply a legal transformation, and I get something which is not a quantum state. Then what do I do with it? Right? I don't have the rules to operate with it. So another way to say, which is equivalent, is that a unitary operations preserve the norm of vectors. Yeah? Preserve inner product. Yeah? So in particular, you can go through the calculation yourself, but these are really very easy implications. You can see that if you apply a unitary transformation on a state psi, you consider the bracket, so the inner product with itself. This is the complex conjugation, right? So we can take U outside and take the dagger. Yeah. Now we use this fact that U times U is identity, and then we know that the norm of the state was 1, yeah, by the definition of a state. So we know that the norm has not changed by applying this unitary transformation. Yeah? So this is the fact that we should remember. Any legal operation is a unitary operation. Okay? So that's how we can sort of change, evolve quantum states. Good? Fact of life. One more thing, okay, that we have to discuss is about the measurement. So now we have talked about these quantum states. We know how they evolve. We know how they change with time. We know what's the rule for a state to be a state. But we are not quantum states. We are classical humans. We are macroscopic objects. So we don't interact with quantum states. We don't see quantum phenomenon on our day-to-day basis. Yeah. So what we see, actually, we see probability distribution. We see bits. Yeah. That's what we know how to operate. And so we need a way to actually connect a quantum state to a classical probability distribution, which is something that we know actually how to operate on. Yeah, and this is called the measurement operator. So fortunately for us, the physicists in the previous century have developed a set of rules that actually determines what happens when a state is observed by a classical observer, by a macroscopic observer like us or our classical computers. Yeah? And once again, not a theorem, but a rule. Yeah? This is the Born rule. So this rule determines what happens when a quantum state interacts with a classical, with a classical observer. And it gives us a way to essentially connect quantum state to our good old classical probability distribution that we all know and love. Okay? That's again a rule, not a theorem. It's the last rule that I'm going to impose on you, and then we can sort of prove things. Okay, so what's the Born rule? First of all, before actually showing you what this Born rule is, let me say that one small remark, that actually any measurement on a quantum state not only gives you some information, but it also changes the state in some way, which is, the way is of course determined by the Born rule, which I'm going to explain in a minute. But this also actually implies that in quantum mechanics, it doesn't really make sense to talk about a passive observer, right? Even the act of reading something, yeah, it's an active, action. So we need to describe what happens when we do this, okay? So rather than actually formally defining what the Born rule says, I will just go by example, and I'll show you what happens when we quote-unquote measure a qubit in the computational basis. Yeah? So if we take a qubit of this form, again without loss of generality, what we obtain by measuring, we measure 0 with probability norm of alpha square, yeah? And 1 with probability norm of beta square. Yeah? And again, the fact that their squares sum up to 1, it means that this is an actual probability distribution. So everything is restored. Right? We don't get anything strange. So all probabilities do sum up to 1. The strange thing, though, is that after I measured, yeah, the state, quote-unquote, collapses to my observation. Yeah? So if I apply the same measurement again, I'll keep on seeing the same result with probability 1. So my measurement has changed the state. Yeah? So my state, it was this. Let's say I see 0 with this probability, and then my residual state is actually 0. So if I observe it again, I get 0 all the time. I don't get to roll the dice again. That's the Born rule for single qubit states. As I said before, small technical point. Typically, when we talk about measurements, we talk about measurements in the computational basis. So we have outcomes associated with the little numbers in these computational basis vectors, either 0 or 1. Yeah? There is nothing holy about computational basis. One can actually measure the state in any base they want, provided that you can do this measurement efficiently. But it turns out that is actually saying that we measure something in the computational basis is actually without loss of generality. That is because we can always do a change of basis for the state, which is a unitary operation. That's something we are allowed to do, and then measure in the computational basis. Yeah. So in theory, computational basis measurements are all you need, provided that you can do do arbitrary unitaries. Sometimes it will be more convenient to say we measure in this basis, we measure in the other basis, but in your head you should think of it as do a rotation first and then measure in the computational basis. These are mathematically equivalent, up to sort of relabeling of the outputs. Yeah? Yeah? Good. Okay, so this was the Born rule for 1 qubit, but we are not actually restricted to single qubits. In fact, we can actually do the so-called partial measurements. So if we have multiple qubits, we can just do some observation on a subsystem of the qubits, and in that case, we have to see what happens to the residual state. Yeah. The sort of intuition here is that once we observe a particular outcome by measuring something on a subsystem, the residual state would collapse with all the states which are consistent with the thing that I've observed. Yeah, sort of the intuition. And I have to renormalize everything so that my state is still a state, so it's still a unit. Yeah. So for instance, consider the following 2 qubit states. What happens if I measure the first qubit? I will get either 0 or 1. Maybe someone wants to try to tell me what's the probability I get 0. About half? It will be in terms of alphas. Say? Fantastic, yeah, exactly. So it will be the sum of these 2 amplitudes. Yeah, the norm of these 2 amplitudes. Yeah? Because those are indeed the states which are consistent, quote unquote, with the observation being 0. Yeah? And again, don't be scared by this is just a scalar factor, it's just used to make my state a unit again. Yeah? So really, if you don't care about normalization, you should think of this part of the state being completely removed and you are left with this, which is everything that is consistent with 0. Yeah? And of course, the same is true for 1. Right? So now I remove this part of the state because I remain with everything that is consistent with 1, and I sort of renormalize everything so that it is still a unit. All good? This is the Born rule. I just show it for 2 qubits, but you can generalize it to any qubit, any amount of qubits that you want. Sort of, I leave it to you as an exercise. Okay? Good. Let me show you one cool thing, small cool example. Now that we know all the rules of quantum mechanics, there is actually something quite strange about quantum mechanics that is actually a consequence of these rules. The fact that it is actually in general impossible to clone states. So if I'm given one copy of a state, it's impossible. This is actually a theorem. It is impossible to create 2 perfect copies of a given quantum state. Yeah? Again, this is of course very different from classical information. If I'm giving you a variable, it's very easy to copy this variable. This is the command to copy it. We do it all the time. Okay? Okay, so to see why, let us consider that there was a quote-unquote ideal cloner. Yeah? So again, now we know the rules. The rules are that we can perform unitary operations on states. I'm ignoring measurement for the moment because the proof is a little bit more complicated if you take measurements into account. So let's just consider unitaries. Cut me some slack on this. So I consider 2 states. This is my state psi. This is some arbitrary basis state. And let's say that there exists this unitary that maps this to this and this, which is 2 perfect copies of psi. Okay? Let's say that this is true. Well, actually, you can actually write down what happens. This actually implements the following mapping by just writing down what the state is symbolically. We can see that U maps this to this, and this is a non-linear operation. Yeah? In particular, this means that it's non-unitary. Okay? So this contradicts the second rule of quantum mechanics, which is you never talk about quantum mechanics. No, it's every operation is a unitary. Okay, so in particular it must be linear, right? So and this tells you that that this unitary cannot exist. Okay. Okay. Good. Okay, so now we have all the set of rules. Now let me stress that from this point on you are fully autonomous. Yeah. So you now have all the materials, all the tools needed to do quantum algorithms. You can rediscover factoring. Now you have all the theoretical tools that you need. So these are the 3 rules of quantum mechanics that we can apply to our computational model and see what we can compute in this model. So let me just a brief recap before going into the model. The first postulate was that any quantum state is a unit in some Hilbert space, complex space of dimension n. Yeah? Quantum states evolve according to unitary operations, so the only legal operations are unitary operations. And the third thing is that the probability of measuring a quantum state yielding a particular result is described by the Born rule. Also what happens to that state after you measure is also described by the Born rule. So these are our 3 rules. And now that we have set this in stone, we can see how and what we can compute with this. Yes?
Do you verify the efficiency? How does efficiency be?
It's a fantastic question, but we will talk about this now. So at the moment, let's not think about efficiency. Let's just think about the model. Yeah, what can we possibly compute in this model? Good. So first of all, we would like to compute at least classical functions. Yeah, like could we use the rules of quantum mechanics to do good old classical computations? Yeah, you have a function, you want to compute it. Okay, so let's try to make it more quantum mechanical, this description. So say that we have a function of this form, that maps n bits to n bits. Can we compute it using the axioms of quantum mechanics? So in more quantum terms, we want to find a unitary operation that implements f in the sense that it maps the basis state x to the basis state f of x, right? These are all bits, right? So this is potentially well defined. So let's try to do that, yeah? So we can think about it for 1 minute, but you will see immediately that in order for such a unitary to exist, f has to be a bijection. So if s is the constant function, for instance, it returns always 0, then it's actually very easy to prove that no such unitary can exist. And again, it's very simple, but the point is that if, let's say, U has collisions, so if f is not a bijection, so it means that it maps 2 basis state to another basis state, like to the same basis state. So this means in particular that U is not full rank, and it does not have an inverse, so it's not unitary. Okay? So again, a necessary condition is that f is invertible, not necessarily efficient, just invertible. And this turns out also to be a sufficient condition. So it's really an if and only if. Okay? I will not show the other direction, but it's just keep in mind that these are necessary and sufficient conditions. Okay, so this actually turns out to be a purely classical question. We can forget for the moment about quantum mechanics and think what functions, what classical functions have such a bijective or reversible implementation. Yeah? Unfortunately for us, this is a question that is well studied, even before people took seriously quantum computing as a discipline. I will not talk too much about the context, but let me just say that it is true that not all functions are reversible. For instance, like it's pretty easy to see that the end function is not reversible. Yeah, if you get the output 0, you don't know whether it came from 0, 1 or 1, 0 or 0, 0. Yeah, so it's not, you lose information by going to this end. So this function is not reversible, but the not function is reversible. Yeah, so if you start from 0, you know you came from 1 and vice versa. Yeah, so although not all functions are reversible, what is true is that all functions can be compiled into a reversible circuit. Yeah. So the answer is actually that we can actually compute all functions, provided that we sort of compile them appropriately into reversible functions. So what I'll show here is actually the Toffoli gate So the Toffoli gate is a reversible version of the NAND gate. You can see this by setting the variable c to be a constant to equal 1. So this implements exactly the NAND gate. But it's more convenient for us because it's actually its own inverse. So if you apply this again, you return with the same input. So this is in particular means that it is reversible. Yeah. So now we all know that NAND is actually universal for classical computation. Now, if you know how to do a reversible implementation of the NAND, it's actually not that hard to use this particular gate to do a reversible implementation of any function. You have to sort of stitch the wires together in the right way so that no information is lost, but you can do it. And in fact, just a constant, I think even about twice as much Toffoli gates are sufficient in order to implement reversibly any function consisting only of NAND gates, which is without loss of generality. Okay? So this is good. This is what we want. And as a corollary of this, in fact, it's more of a corollary of the proof. If you do it, you'll see why. We know that any classical function actually admits a unitary implementation. And as a corollary of the proof, we know that if f is efficiently computable, then so is unitary implementation. I will sort of swipe a little bit of details under the rug, but this is true. So in particular, we can say that there exists a unitary u sub f such that it maps this state to this state. Yeah? So now we know that we can measure states, so measuring this guy in the computational basis will give us the output of our function. Yeah? So we have just shown that, using the laws of quantum mechanics, we can actually compute any function that we can compute classically. Okay, and furthermore, it is quote-unquote efficiency preserving. One small remark, in order to make this transformation unitary, yeah, I had to add this register here. Yeah, that's called, sometimes referred to as the ancillary register. This is a bit strange. It is not something that you would do with classical computation, right? So, I mean, this is just to, it seems like a technicality, but turns out to be actually pretty important in some contexts. You have to add register so that dimensions is preserved, and this actually is implemented through a reversible, in particular, a unitary operation. Yeah. But one thing that is true is that there is actually nothing special about the zero state. Yeah, we can actually put our favorite basis state. Yeah, in fact, we can even put any state here and define the action of this unitary on a state via their computational basis action and implement this mapping. Yeah. So this is true, and we can prove this. Yeah, I haven't shown you the full proof, but this is true.
So my question is, if we use the identity function, then, I mean, at first glance, at least, it looks like you can do copying, but before you told us that we cannot do it. So I mean, identity function just here, it would just map this to the same state. So it would map x0 to x0. Copying would mean map x0 to xx. So copying it means not to find a copy of the same state, but two copies. So let me actually quickly go back and show you. So see, the identity function would map this to a 0. But if we just apply to the first part and then we have some zeros afterwards, then we have the result is still x and then f of x, and f of x is the identity function, so we have x and x, right? So we turned x and those
good,
zeros.
Good. I see what you mean. I see. So you mean f is the identity, not the unitary. Yeah. I see. Good. So that works only for basis states. So it only works for states which are, it is true for classical states. right? So indeed, it matches our intuition that we can copy classical states.
Okay, yeah, okay.
But,
yeah,
but
I see.
Makes sense? Yeah.
Thanks.
Yeah, perfect. Yeah, excellent point, actually, yeah. So, good. It would have been strange otherwise because we know we can copy classical information, right? So, yeah. Okay, okay, maybe one thing I should make more clear is that I'm defining the unitary on basis states, but by linearity, this definition extends to all states. Now, of course, what happens to the state will depend on the amplitudes, will depend on the support of the state, and you would have to calculate it through this transformation. But like this is my definition of the unitary. I can define it without loss of generality to act on just on basis states. But it doesn't mean it's copying the state. Good point. Okay, so now a little bit more in complexity theoretic terms. What we have just shown here with our theorem is that any function that is efficiently computable classically is also efficiently computable using the laws of quantum mechanics. Yeah, and again, this is P is, of course, we all know is the class of functions which are efficiently computable classically, and BQP is an ugly name to denote the functions that are efficiently computable using a quantum hardware. And it stands for bounded quantum polynomial time, bounded error quantum polynomial time. It's not very important why this acronym is defined the way it is, okay? But we know at least that this computational model as we define is at least as powerful as the classical in terms of, efficient functions, okay? And now we can ask the reverse question, yeah? Can we classically simulate all the functions that we could compute using a quantum computer? Yeah, it's a perfectly valid question. And, there is something magical about quantum, there is entanglement and so on, so one may actually be tempted to believe that this model is infinitely more powerful than the classical model of computation. So actually this is not the case, okay? So it's known, and it's actually not that hard to prove, that we can simulate any function that we can compute with a quantum computer with a classical computer. Of course, the catch is that it won't be an efficient simulation. So you need all the power of P space in order to simulate a quantum computer in general. So that's what we know how to prove. Yeah. Actually, the proof is not that hard. You can, think a little bit for yourself. Essentially, the idea is so if you don't restrict yourself to polynomial space, it's super easy. You can literally just do this, computation, this large matrix computation on your classical computer. Of course, it will take you a long time, but you can do it. If you want to restrict yourself about polynomial space, you have to think a little bit harder. You can use Feynman path integral if you're a physicist, or you can just look at it and you'll find the right answer by looking at it. Okay, again, the catch, of course, is that this simulation is inefficient. We are not claiming efficiency here. We're just claiming that, in principle, we can simulate everything. So there is a point in which quantum computing becomes useless. Yeah? Okay. Okay, fine, but what we're really interested in is the question whether all quantum computation can be efficiently simulated by a classical computer. That's the question that we really want to know. Yeah, we don't care about inefficient computation. And okay, and that's sort of the million-dollar question. I mean, we believe that the answer is yes. So there are quantum computation that we cannot efficiently simulate on classical computers, but of course we don't know how to prove it. But we have sort of good evidence for this to be the case, and we'll see more in the next talks. Now, for the moment, I'm just happy to make a little bit more precise what I mean by efficiency, right? So we have to work a little bit harder. Efficiency in the classical setting is just, at least in the circuit model, you just count the number of gates. Yeah, that's sort of the way you measure the size of a circuit. That's one way to define efficiency. Turns out you can do essentially the same for quantum computers. You typically define your computation as a quantum circuit, and the way you measure efficiency is by counting the number of small gates that this circuit consists of. Now, of course, it's a quantum circuit. So by the laws of quantum mechanics, each gate here will be a smaller unitary. So it will be a little constant size unitary that we apply on certain registers of the system. So these are all little unitaries, yeah, that we apply on the state. And of course, together, combined in this way, they form a larger unitary, which I'm calling U star. You can convince yourself by looking at this that composing unitaries this way still give you a unitary. It's not a hard proof. And the way we do the computation is essentially by stitching together our state in this register. Of course, we'll need one register per qubit of the state. Yeah. Sometimes we'll need also this, what I call ancilla, so we just leave some space for the zero state, and then we pass it through a series of unitary operations, and we track the evolution of a state throughout the circuit. Yeah? These are all little unitaries. Once the state reaches this stage, we can apply some measurement. This is, by the way, the symbol for the measurement. The symbol for the measurement in the computational basis. Yeah, and from that we get some result. That's our circuit model for computing. Yeah. So in a sense, much like the classical model, we obtain big unitaries by stitching together little constant size unitaries.
That's not the interactivity, like after the measurement we have and you get the zero on the non-measured part, increase computational power.
Say again? Sorry?
You could imagine a model when you could make measurements in the middle.
Good.
Depending on the measurements, you add a new gate on the unmeasured.
Fantastic question. That actually turns out to be exactly the same model. You can think that without loss of generality, all the measurements are in the very end of the circuit. So there is a way, which I don't want to talk too much about, but there is a way to sort of take any circuit with measurements in the middle and push all this measurement to the end of the computation, and you will get exactly the same result. As long as you don't care too much about space. But in terms of like, P versus BQP would be the same complexity class. It doesn't change the complexity class. Would you confirm?
I was going to ask, related to this, if you can expand on why we can perform one measurement rather than a measurement on all registers.
Say again, repeat the question.
So could you explain why here, for example, we can perform just a single measurement rather than a measurement on all registers?
So, I mean, the way I define the Born rule, you can measure any subsystem of my qubits, of my quantum states. Yeah. In this case, I decided just to measure one qubit. Maybe I was just interested in one bit of output. But again, nothing stops me from measuring more than. It just really depends how much information I'm interested in. Now, of course, what will happen to the state after I measure, I would have to calculate using the rules that I defined before. But so there is nothing, again, maybe there is nothing special about having just one measurement gate. You can have as many as you want, depending on what you're interested in.
I mean, yeah, like how I understand it also is that if, for example, you have entangling gates throughout, and
you have a what? Sorry.
Entangling gates.
Entangling gates, yeah.
Then, if your entangling gates are on the last qubit as well, and if you measure the last qubit, then you're getting information about the other parts of the system as well, right?
Sure.
Yeah.
I mean, that would sort of follow from the axioms that I showed you before. If you do the calculation, you check how the amplitudes cancel out, you will see that you will get some information also about
Yeah. Okay.
But again, without loss of generality, all circuits are more or less of this form. Yeah. Consisting of small unitaries in the middle, and then some measurements in the end.
So, and what happens when we combine this with classical computation? So can we so if we do this, measure something, and then we need to run some classical computation, can we just set up the initial states to any quantum states we want? Can we think of it like that I can...
So as I showed you before, actually any classical function can be computed using a quantum circuit. So I could just think of part of this circuit as computing my classical function, and that would be without loss of generality.
More like, because as far as I understand, most algorithms still would like to use some classical computation for certain tasks and combine these two, but So I'm just it's more from the practical point of view.
The practical point of view.
If we were to kind of factor integers or something, probably combine quantum computer.
Yeah, no, I don't know. I mean, you know, once you measure something, this is classical, and then of course nothing stops you from.
So I can set up these initial states on the left-hand side. I can set them up to any quantum states.
But provided you know how to prepare it. I mean, if you're talking about practical,
okay,
I mean,
it's more practical, but not going into all the details. But
not so practical. Okay, so in principle, you can put any state that you want, provided that you know how to prepare it, and you can compute any unitary. In particular, again, if you're interested in a classical computation, nothing stops you from doing it this way, although it would be maybe not the most efficient one.
Thank you.
My question is, what is the physical representation of gates? For example, in classical we have transistors, which things we could put in quantum.
Good. No, that's the physics part of the talk, which I you know don't want to talk, and I don't know much about. What I can say is that much like classical computation, there is no just unique way to do quantum computation. There is not a unique way to do quantum computation. There are like many physical systems that you can use to simulate this kind of operation. This is just an abstraction that is useful for us to reason about algorithms, but you can implement it in different ways. I mean, but maybe some of the more informed people can say more about it. I don't have much information.
Just wondering about, for example, simplest examples, or at least one example of such kind of.
One example? No. You forget about reality. So this is our model. No, it's counterproductive to me. No, we can discuss offline, but maybe let me not go there now.
Thank you.
There's a question there.
Can you give some intuition on what input states we can prepare on the left side? That's also a physics problem.
No. So I know that's a good question actually. So you can either think of, you're given a state from God and then you start computing of it, but then of course it's it doesn't answer your question. Actually, it's an interesting question, what kind of state you can prepare efficiently, yeah? And the way to answer this question is unfortunately a bit circular. It would be to say, okay, let's say I start with the all zero state here, I run it through a quantum circuit that looks like this, and the state that is here, maybe without even measuring, would be the state I can prepare efficiently. Yeah. So it's literally just a circuit that prepares a state for you.
Okay.
There are many examples of quantum state that are easy to prepare. For instance, the EPR state, as I showed you before, is just like just two gates, two simple gates that I'll show you in a minute. But in general, there is no succinct description of what kind of states we can prepare efficiently, just because the definition of an efficient preparation of a state is once again a quantum circuit that prepares this state.
And is there like a limitation on what we can actually prepare? Like
in physical reality? No, so that goes more in the part that I don't want to talk about.
Okay. Thank you.
Maybe one can add that for BQP, we want to restrict the input to be 0. Or, the instance, the problem instance.
Yeah. So okay, what Chris is saying is that technically the class BQP, the same way as the class P is defined, the class BQP is defined is without loss of generality. You take the entire input state to be 0, yeah, and then you measure the last register of your computation. But again, nothing stops you from plugging in another state in this model. Yeah. So maybe last question, and then we try to move on, because otherwise I don't get to finish.
Could you please clarify for the audience how much information can we extract from this quantum circuit or from this quantum state? How much classical information can
That's the million-dollar question. Okay, so okay, how much classical information? The boring answer is as many bits as you're measuring. Yeah. So in this case, I will extract exactly 1 bit out of the output state. Now, what is this bit? I mean, it can be either a random bit, which doesn't mean much, or a very important bit like, I don't know, it's an example of a very important bit. Tomorrow is going to rain, yes or no? Yeah? That could be like useful information to have. In general, there is no nice and succinct way to show, you know, what you can extract out of a state, rather than appealing to the rules that I showed you before. So you have to really look at the state, apply the Born rule, and see what happens. There is no general formula to, you know, extract useful information out of a qubit. I mean, it also depends what you mean by useful. Does that make sense?
No, I just wanted to recall this Holevo boundary that it is not possible to extract more than n classical bits from n quantum bits.
I see. Okay, so that's where you were going. I see. So I think maybe that's a slightly different setting. You're saying, you know, how much information I can store into a quantum state. Yeah. So you would, in principle, think that state, you know, it has this gigantic Hilbert space. You can pack a lot of information. Turns out that there is a result in information theory. It's called the Holevo bound, that essentially tells you that no matter what you do, you will not be able to pack more than n bits into an n qubit quantum state. You know, unless you have entanglements. But let me not go there. But yes. Good. So there is a sense in which a quantum state cannot pack too much classical information. But there is also another sense that the useful information that we can extract is a little bit more than what you can do classically, right? So this we'll see in a bit. Thanks.